So welcome everyone to today's webinar, towards the circular economy of electric vehicle batteries. Today we are joined by Gavin Harper, who helped to establish the University of Birmingham Centre for Strategic Elements and Critical Materials. He is currently a research fellow with the UKRI Interdisciplinary Centre for the Circular Economy of Technology Metals. Today's webinar will explore the current state-of-the-art technologies used to process electric vehicle batteries and ask participants to consider what needs to change as the industry scales into the future. It will also look at the future demand on the critical raw materials used in electric vehicle batteries and how effective end-of-life management can assist in ensuring resilience for Western automakers by providing a source of key raw materials for battery manufacturing in the future. As always, there's a chance to ask questions. I'll ask these on your behalf, so please submit them in the Q&A option at the bottom of your screen at any point during the presentation. Thank you for logging in today, and I'll now hand over to Gavin.
Thank you very much, Derek. So let's just bring my slides up. So towards a circular economy of electric vehicle batteries, as Derek said, my name's Gavin Harper. I'm a research fellow on the MET4Tech project that's looking at a future circular economy of technology metals in the UK. And I'm also part of the Birmingham Centre for Strategic Elements and Critical Materials. And just to tell you a little bit about some of our work, so we set up the Birmingham Centre for Strategic Elements and Critical Materials in anticipation that the UK was going to be leaving the European Union and that there would be a need for sort of bespoke UK policy in this particular area and unique technology solutions. So we set up the CREAM network, the first academic network focused on critical elements and raw materials. We host the Faraday Institution's ReLiB project on the recycling and reuse of lithium-ion batteries, one of the largest UK projects in this area. We do lots of work in terms of media engagement, wide array of different battery projects, also some work on recycling rare earth magnets, and we've got lots of high impact scientific publications. And in particular, one of the areas where we've tried to provide some leadership is in this area of critical materials and UK strategy. So we released this policy commission, which you can see in the bottom right hand corner, Securing Technology Critical Metals for Britain, chaired by Sir John Beddington. And that was really a piece of work that started to articulate what we should be doing in the UK, how we should be doing things differently. And actually some of those recommendations have been taken up by government. We've seen the launch of the Critical Materials Intelligence Centre and a whole range of different investments to try and improve the UK's position in this domain. But why do we need to do that, and how does that feed into a circular economy of critical materials? So we've published this paper in 2019, and we're very lucky in that it was featured in the 150th anniversary issue of Nature, and so this paper has received an enormous amount of attention. And this was really our baseline survey of where were lithium-ion battery technology for recycling at this particular point in time. So a snapshot of what the industry was doing and what the potential future routes were. And we've been developing this position since 2019 with our own research and really trying to sort of forecast into the future and think about what that needs to look like. And so we've got a forthcoming roadmap with JFIS Energy, a roadmap for a sustainable circular economy of lithium-ion batteries. And some of the ideas in that roadmap, which is going to come out soon, are featured in this talk. And so really, the driver for this is that we've got massive anticipated future demand for lithium-ion batteries. And that's in large part driven by the sort of switch to passenger electric vehicles. So that's the bulk of the demand. We also see a significant number going into commercial and larger scale electric vehicles. And there's also going to be significant demand for stationary storage. And one of the things I'd like you to sort of keep in your head is this idea that you've got a sort of scale of the battery times by the volume of potential future sales. So for example, with consumer electronics, they're abundant. We see loads of mobile phones, laptops, tablets, and etc. But the batteries contained within them, although the sales of the units are incredibly high, the batteries in them are rather small. Whereas by contrast, the reason that chunk for passenger EVs is so big is that the batteries inside those EVs are of a significant size and the market is also quite big. So it's that sort of multiplier effect. And again, you know, with commercial EVs, the battery packs are that much bigger, but the volumes that we anticipate are, you know, relatively small compared to passenger EVs. And we can see that if we sort of segment this by market, you know, the UK there in dark blue is a significant market, but we see, you know, massive markets in China, the United States, Germany, etc. If we break this down globally by where we expect these electric vehicles to be sold. So the UK is a significant market, but obviously there are going to be much bigger ones around the world. And what we've seen is this trend of a sort of year-on-year change with, you know, consumers really responding to the drivers for purchasing electric vehicles, lots of things to make them more attractive. Obviously, we've had a recent announcement that people are going to have to start paying road tax on EVs, but you know, there have been a array of different incentives to encourage their uptake. And we've seen conventional petrol and diesel sales start to fall, battery and hybrid sales start to increase. And obviously, you know, manufacturers have all on the whole announced their plans to pivot to electric vehicles in the years to come. And so this was a projection from the Faraday Institution. On the left-hand side was their initial predictions around what UK EV production would look like relative to the total UK production of vehicles. And on the right was something that I actually prepared myself, mindful of the fact that there were government targets to phase out conventional vehicles, and then those targets were brought forward. And in actual fact, the Faraday Institution have since released an update to this graph, which is very, very similar to what I've sort of put together here. So we can see with that UK production in the years leading up to 2030, you know, with the phase out of internal combustion engine vehicles, we start to see that pivot to EVs dominating the market. But we've got a challenge, and that's a sort of, you know, industrial strategy challenge. That if we look at the UK and Europe and the West relative to other countries around the world, you know, benchmark mineral intelligence are tracking the development of gigafactories around the world. And you can see that, you know, year on year, there have been massive increases in that diagram in the bottom right-hand side in the number of gigafactories developed and announced. But we can see, looking on the map, that the bulk of all of these developments are taking place in China. And you may have seen on the news recently about the travails of British Volt. The Faraday Institution have said that they anticipate that we're going to need, you know, around 6-7 gigafactories by 2040, and we're struggling at the moment to get one off of the ground. And so this is a real challenge because, you know, people, automotive industry analysts say that unless you actually got the battery manufacturing industry located in the UK, we may struggle in the future to retain the automotive industry. And obviously that comes with a whole bunch of attendant job losses. So there's a sort of industrial strategy reason for trying to secure the critical raw materials needed for batteries. But then there's also an environmental and waste management issue at the end of life. Now, one of the challenges that we've got is that predictions really vary as to what the future cathode mix of batteries is going to look like. So lithium-ion batteries is an umbrella term that applies to a whole range of different batteries. And one of the things that differentiates those batteries is what we call the cathode mix. And you can see on the bottom left-hand side, the Faraday Institution's projections around how they anticipate the future cathode mix to evolve. I've highlighted in red the projections for LFP because I'm not very confident in these predictions myself. And since these were announced, there've been a whole range of different announcements from automotive manufacturers to say that they're looking at LFP as a technology. So just to unpick what some of this means, NMC and NCA batteries, nickel, manganese, cobalt, and nickel, cobalt, aluminium. So these are batteries that have got very high energy performance. It can store an awful lot of energy in a small space, which gives you a really good range to vehicles. But the flip side of that is that they're reliant on critical raw materials, particularly cobalt and nickel. And cobalt, there are particular problems because the bulk of it is sourced from the Democratic Republic of Congo, as we'll see. So it's a challenge securing the materials for these batteries. The materials are expensive. By contrast, LFP batteries are what some people have sort of referred to as rust and fertilizer batteries. So lithium ferrophosphate, iron and phosphate, relatively common and abundant materials, but you have to put a lot more work into processing that material to make them. So there's a lot of energy investment in LFP. Now the challenge between these two is that for NMC and NCA, it's relatively easy to recover value because the materials within those batteries are intrinsically valuable. So we can use some quite crude processes to extract value from those batteries at the end of life. With LFP, it's different and it's challenging because the materials are intrinsically very low in terms of their value. And so you can't just recover the raw material, you actually need to be able to try and recover the material in a higher value state. And we'll look at a bit of this as we go on. And if you just look on the right hand side, that's some projections by Wood Mackenzie, slightly more optimistic in terms of the share of LFP, especially in energy storage deployments. The one thing going back to the graph on the left that I've noted, you see at the bottom the colour code for NMC 111, 622, 811, 9.5.5. What that's referring to is the sort of ratio between the nickel, manganese and cobalt. And there's attempts over time to try and pivot from very high cobalt chemistries, which is the NMC 111, to ratios whereby there is less cobalt and more nickel in the future. So if we look at where these materials come from around the world, we can see that the location of the primary resources, depending on the resources distributed in different places. China have got a real monopoly on the production of graphite. Democratic Republic of Congo have got a real monopoly on the production of cobalt. Lithium tends to be concentrated in South America and Australia. Nickel, there's a little bit more of a spread, although there's some vulnerabilities with nickel being produced by Russia. And this is just the location of the primary resources. But the challenge that we've got is that China has managed to secure a real monopoly on the processing capacity to take these primary resources and convert them into useful materials. So in terms of industrial strategy, it's something we need to consider going forward. And you can see here, in terms of cobalt production, Congo really dominates, and Russia is a very, very, poor second place relative to all the other countries. So there's real challenges, especially in the way that some of this cobalt is produced. There's concerns, ESG concerns around artisanal and small-scale mining and some of the environmental impacts of that industry and how that's regulated. So, there's significant challenges here with that monopoly position. There are obviously some well-regulated mining companies that work in that space as well, but manufacturers have got to be, particularly careful in terms of their, procurement strategies and supply chains to ensure that that cobalt is being sourced in an ethical way. And we can see that over time, production of cobalt is massively ramping up. And there's some projections from the International Energy Agency, which are really quite shocking around how much our production and materials will need to gear up in the future to transition to this sort of clean energy future. And so we've also got to consider that within the whole life cycle of lithium-ion batteries, what do we need to think about? Well, there are safety concerns over the whole life cycle, but especially at the end of life. So we're looking at ESG concerns at the start of life and the mining and production of materials. But we really want to think about if we're going to produce secondary materials from recycled goods, we need to make sure that these also meet very high standards. And so there's a whole range of different safety systems that are intrinsic to batteries around the battery management system, physical safety, thermal cutouts, barriers, fuses, chemical additives that are added for fire retardant purposes, and some sort of intrinsic functional bits of the battery like solid electrolyte interface that contribute to safety. But we've got these whole range of risks around processing batteries at the end of life that need to be managed carefully. And so when we sort of developing recycling systems for the future, we want to be really mindful of all of these different risks and make sure that future systems take account of these. And so, people are familiar with the waste management hierarchy on the left. This idea that it's good to reduce the amount of materials used, first of all, and then, move to reusing whole components. And then the concept that, there's this cascade after. So recycling is the next preference, energy recovery after that, and finally disposal if we're really faced with very few other options. And one of the things that we introduced in our Nature paper was to say that within recycling, we can't just consider recycling as a black box and a universal good. We need to realise that within recycling, there's this whole spectrum from, you know, very good advanced processes to very crude, less good processes. And within this spectrum of different processes, we obviously want to try and drive the industry towards more advanced processes where material streams possibly become less mixed and less contaminated, which leads to more materials being recovered and higher value of materials being recovered as well. And so if we look at the end-of-life vehicle industry as it stands at the moment, there's sort of one technology that vehicle manufacturers are really reliant on, which is shredding. And this idea that, you know, we take a vehicle, we take out some of the key components, you know, decontaminate it, take the fluids out, etc., take the tyres off, take the battery out, and then the whole car just goes into a shredder. And shredding is really good because it sort of regularizes everything. It breaks it into smaller pieces, which are easy to handle. And we can then take those smaller pieces and those shredded materials, and we can use a whole bunch of different separation techniques, including magnetic separation, eddy current separation, you know, and sort of using air and different screening processes to separate the ferrous metals, the non-ferrous metals, and then obviously all the fluff and the sort of plastics and things in the dashboards and seats. And then from that, you know, we end up with a whole range of different bins of different materials that can then potentially go into future recycling. And this is really elegant because it's simple, and you know, you can take a wide variety of different things and it will regularize those into you know, sort of a range of outputs that are potentially useful. But for critical materials, especially those in batteries, we've got some real challenges. Very different challenge from separating bulk materials. It's not a case of just you know, being able to then take the metal, smelt it, etc. Because we've got very high value materials in small quantities, and they're distributed through you know, the battery and you know, in the case of rare earth magnets in you know, motor assemblies, they're distributed through the vehicle. And actually, if we were to just put them in a shredder, what we'd get out of the other end is something not particularly useful. And so an analogy that I would use with this is to say it's a little bit like if you think about a Victoria sponge and you think about the layered structure of having 2 sponge cakes, some buttercream and some jam in the middle. And if you wanted to separate all of the components of that cake, you wouldn't take the cake and put it in a blender and blend it all together and then try and work out how to get the jam and the cream out of the middle. You take the cake and you probably peel that cake apart, and you would then be able to sort of scrape off the jam and put that in one bowl, scrape off the cream, and that would be a cleaner way of separating that material. And so what we're saying is when it comes to electric vehicle batteries, we really need to take more of this sort of disassembly approach rather than the shredding approach. Although that said, you know, lots of battery recyclers at the moment are reliant on this sort of shredding process, which takes you to a low value state. But we'll consider that a little bit more as the presentation goes on. So we've got a lot of complexity and a lot of variation in the batteries that we find in electric vehicles. So if you look on the right hand side, this is like a Nissan Leaf type pack, and we've got these pouch cells which are sort of squished together mylar cells. We've got like a layered structure. They're very flat. They're potentially quite easy to recycle relative to some of the other types of batteries. We've got in the middle a BMW prismatic cell. So this is where you've got sort of square rectangular cell with quite a hard case. And so we've got all of the battery materials inside. The case is rigid. It's a slightly different form factor. And then on the left hand side, we've got sort of more of a Tesla type pack using cylindrical cells, which are sort of tightly wound coils of material. And what I'd say with the cylindrical cells, I mean, from a recycling perspective, they're a little bit of a nightmare. If you think about the sort of Victoria sponge analogy, and then think about sort of translating that to Cadbury's mini rolls and trying to disassemble Cadbury's mini rolls and separate them out and separate the cake and the filling, etc. And you know, in a big Tesla pack, you know, you've got 16 modules. Each module has got 444 cells. You know, it's a lot of little Swiss rolls to be trying to disassemble. And so for that reason, we think that probably the better form factor is larger battery packs that are flat and linear. And so what we haven't got on here is that there is a new battery by BYD, the Blade pack. It emits this intermediate module stage. And so it consists of very large cells, which just fit straight into a pack. And we think potentially that could be great for the future of recycling. And so if you look at taking a pack apart and separating it into those, you know, individual modules, individual cells, and then separating the cells into the individual electrodes, you know, there's a lot of complexity at each stage of pack disassembly. And we need to think how to manage that complexity when we're developing new recycling processes. And so if we were to contrast the sort of current approach of recycling batteries from what we'd like to see in the future, at the moment we take a battery, we shred the battery into shreds, and then we end up with a bunch of mixed material, different anodes and cathode materials. And then from that we have to delaminate the active materials from those shredded bits of aluminium, copper, and a bit of mixed plastic. And that gives us something that we call black mass, which is a mixture of all the sort of anode and cathode materials. But separately, we have a bunch of shredded foil, aluminium foil, copper foil, and plastics, etc. And then we have to take these two bunches of materials and further separate them. So we mix everything up to begin with, and then we've got to try and work out how to separate things as we go. Now, in an ideal process, we think about how to do things more efficiently by separating everything bit by bit, separating the anode and the cathode first of all, and then delaminating that material, keeping it all separate, keeping it all as clean as possible. And that leads to better environmental outcomes down the line because we're able to cleanly separate the materials, keep them segregated, you know, and then that leads to purer materials in a higher value state. And we think that this is the way forward. And so at the University of Leicester, they've developed this technique around ultrasonication. And so this concept that, you know, if you had these electrodes and they were in the form almost a bit like a Christmas cracker, where you could pull them both apart and separate them. And then once you've separated the anodes and the cathodes, you pass them through this process with something called a sonotrode. And it's a bit like if you think about an ultrasonic jewelry cleaner, how it gives you very high intensity ultrasound vibration that lifts dirt off of a surface. It's sort of doing this on a more industrial scale with the materials and the foils. And so what you get out of the end is a very clean foil, and then obviously the active material settles, and we're able to take that on for further processing. And you can see some of the results here of the ultrasonic delamination process, where you start off with the sort of electrodes coated with the material, you pass it through this process, and you end up with a very, very clean material on the other side with most of that active material that's you know, been removed. And this is the patent. There's IP protection, and they're currently trying to go through the process of licensing this technology and you know, sort of getting manufacturers to adopt it in better recycling processes. So another thing is that, you know, it's people sort of tend to think of end of life processing as being something, you know, it's an afterthought. It happens at the end. You know, it's the recycler's job to deal with waste. But actually, there's so much that we could be doing early doors to make recyclers' lives that much easier. And so it's our suggestion that, you know, rather than thinking about recycling as this thing that happens right at the end of pipe to deal with batteries that people have made, if we could think about design for recycling much earlier on in the process. So we think about putting lithium-ion batteries together with a view to how they're going to be taken apart at the end of the life. And this could, make the whole circular economy so much better if vehicle manufacturers would take this on board. And so one of the things that we've looked into in this journal, Green Chemistry, is this idea of sort of switchable, debondable adhesives. And so if you think, adhesives, they stick things together, but then when it comes to recycling things, it makes it very difficult to pull apart. Manufacturers love adhesives because they're cheap and simple and they put things together quickly. But then when it comes to taking them apart, it's very, very difficult for recyclers because, it's not a mechanical fixing that can be easily undone. It's an adhesive that has to be unglued or cut apart. And it really frustrates the ability with which we're able to take things apart. And so one of the things that we're saying is actually you can have these smart adhesives where you're able to switch them by applying a stimulus. And that stimulus would either cause the adhesive itself to fail, or even the boundary line between the adhesive and the substrate. And so, on the left-hand side, we've got sort of, normal adhesion. Sometimes if you pull things apart and the adhesive hasn't failed, the actual substrate itself will fail. But then, if you've got these switchable adhesives, you can cause the adhesive or the interface to fail. And so there's a whole range of different stimulus that we could look at. And we need to think about, what stimuli aren't present within the normal operating environment of that battery, and how, if we were to apply one of these to the battery at end of life, could we cause these different adhesive bonds to fail? And so if you look at where adhesives are used in a battery, the other thing to consider is that they are used to provide a lot more function than just sticking things together. Sometimes they're providing electrical insulation, or they're providing thermal functional properties to aid in safety and fire protection, or they're providing a thermal interface in addition to an adhesive function where they're conducting away heat from batteries into cooling systems, or they're providing compression to ensure good contact, and they might be damping down vibration. And so we need to think about all of this as we're designing potential future debondable adhesive systems, and think about these functional useful properties that adhesives are fulfilling, in addition to the sort of sticking together property. And so thinking of how that might look in a future recycling system, and what that might look like, we need to think that there are different types of end-of-life waste, and some of those will just be vehicles that have reached the end of life naturally because they're too old, or they've worn out, or there's been a mechanical failure. And some of those will be damaged as a result of accidents, and those batteries are potentially a little bit more problematic because there could be safety issues with them. But the other thing that we might have is quality control fail cells. And so a lot of the early market for recycling is going to be provided from production scrap, which is to say the factories that are looking to produce lithium-ion batteries in the future, especially when they're finding their feet and starting up and establishing new processes, they get to the point where they end up with a proportion of the batteries that aren't any good, and they need to be, sort of dealt with to enhance the efficiency of manufacturing processes. Now, if it comes to end of life and accident damaged batteries, they're going to be in full packs. And so first of all, the pack needs to be removed and disassembled. And there's a decision to be made at that point. So if you've got a battery that's in relatively good condition, you might want to put it into separating the anodes and cathodes and be able to disassemble that. If it's an accident damaged pack, it might be too problematic to disassemble. And in that case, we'd want to maybe put it into a shredding route. Or if it's got cylindrical cells, they're probably too difficult to disassemble as well. And so that would have to go through this sort of shred, salt, purification route. Now, if we've got fairly clean cells, or we've got production scrap, that's where we might be able to go into a sort of separation process. And here, module design could be really key to ensuring that we're able to take batteries apart easily in the future. And then we'd be able to look at delaminating the material, removing the plastics, regenerating that material. Or if the material's really clean, we might be able to go into more of a direct recycling, recasting process. And there's all sorts of things that we could look at in terms of design for recycling to make things easier to recycle at the end of life. So thinking about, how we open the electric vehicle battery packs, are they stuck together, or are they in terms of, sort of mechanical fixings, etc. And then when it comes to sort of automation, it's thinking about how we might be able to take battery packs apart using robots and robotics. And part of that is thinking about how to make things easy. So can we unify the types of bolts, so that rather than having half a dozen different bolts that require different socket heads, can we rationalize that and use less different things so we have to swap less tools? Can we have any standards? Can we have any universality? Can we have connectors that are easier to remove by machine and don't require a human operative to unplug them because they've got some sort of complex mechanism? That's thinking about all these things in pack design that we can use to try and optimize the design of packs for better recycling down the line. And then just going back to these debondable adhesives and thinking about the sorts of mechanisms that can be used in design for recycling to create adhesives that fail. So some, for example, like the idea of sort of having shape memory alloy. So a shape memory alloy is a metal whereby you can bend it and it will form a different shape. And then you heat that up and you apply thermal stimulus and it causes the metal to expand, return to its initial shape. And that in turn could be used to fracture the adhesive bond. There's also an idea around sort of polymeric nanocapsules that could be embedded in the adhesive, and these are full of a sort of gas that is inside these nanocapsules. And then if you heat that up, it causes the gas to escape from the polymeric nanocapsules, and as that gas escapes, it diffuses through the adhesive, causes the adhesive to fail. And then additionally, there are adhesives whereby you can apply an electrical stimulus and it will cause them to fail. We've got lots of ideas around, ways that we could innovate design for recycled battery packs in the future. And so what this looks like in terms of a roadmap for the future and different recycling technologies, the sort of initial technology that's been used a lot by companies like UKRI is this idea of pyrometallurgy. You stick everything in the furnace and your lithium and your plastics and your aluminium actually get consumed to provide energy for that furnace. So, some of it gets recycled, some of it is into really energy recovery, and we get a relatively low rate of recovery from that sort of process. But it's an established technology, and people like UKRI already have pyrometallurgical furnaces that are used for weed processing and other electronic goods. And given that they're big capital investments, it made sense for them to look at battery recycling. But the disadvantages of that method is that the cobalt and the nickel are very easy to recover. Some of the other components, not so much. Now, the other alternative is hydrometallurgical techniques. And so here you're using solvents and different sort of special things like deep eutectic solvents to be able to recover certain materials selectively. Now, with these hydrometallurgical processes, the more and more selective you need to make the process. So the greater range of things that are mixed together and the more specific the thing that you want to extract, the more complicated the chemistry, and so the more environmental impact that comes with that chemistry if you're having to make a process that is highly selective to extract material from a real mixed bag of stuff. Now, if we could work on that mechanical separation at the front end, sort and separate things in a way that was much cleaner, that would unlock, real enhancements in terms of being able to use less selective hydrometallurgical techniques and to keep that material in a higher value state. And so this is really moving on to recycling 3.0, where perhaps, we're using some of the existing recycling technologies in terms of hydrometallurgy, but by disassembling current cells and taking them to bits, we're able to focus on much higher value recovery by keeping the materials in a higher purity state. And so looking down the line, where would we really want to end up? Or if we could really redesign cells as well as redesigning recycling processes, we could potentially get much higher rates of materials recovery, looking at, not only being able to take them apart and recover some of the high value materials, but obviously in an ideal world, we want to be thinking about how can we recover everything from the whole cell, all of the plastics, all of the separators, all the stuff that would commonly be seen as junk. And so we want maximum recovery in the future that integrates both design for recycling approaches at the front of things and, at the end of life, being able to have much better recycling technologies. And so I see a couple of comments in the Q&As that have just popped up. So I'm going to try and speak to some of these. So Professor Steve Martin asked which of the car manufacturers are taking an ethical approach to ESG, extracting and end-of-life recycling. So I think pretty much universally, because of consumer expectations, all Western car manufacturers are heavily invested in ESG in terms of the mined materials at the start of life. And in terms of their corporate social responsibility and their various policies to comply with that, there's a lot of work that goes into supply chain due diligence. Obviously, they're working with major battery OEMs, and those battery OEMs are particularly focused on making sure that their feedstocks for their materials are ethically sourced. I couldn't give you, an exact representation. Obviously, there's a whole study there in terms of car manufacturers' approaches to ESG, which could be done. Something that would be interesting taking part in if that was of interest to you. In terms of end-of-life recycling, again, in the West, there are really strong regulations around how end-of-life vehicles have to be treated and disposed of. And so I think that, as soon as your vehicle goes to an authorised treatment facility, it enters into a chain of custody where things have to be done correctly. I think perhaps, globally, where there are some more reservations might be around, not so much a problem for the UK, because our steering wheel's on the other side from a lot of the rest of the world. And so we tend to recycle a lot of our vehicles in the UK. But certainly in continental Europe, there are export markets for European vehicles to Africa, other countries where perhaps there is less capacity to responsibly deal with waste at the end of life. And so, if vehicles leach out as a second-hand product from markets where things are well regulated, markets where things are less regulated, I think that there's potential, for things to go amiss. What I would say is that whilst perhaps there's, how might we say, more flexibility in China, less expectation in some quarters around things like ESG concerns, because the Chinese vehicle and recycling and materials processing industry is so vertically integrated, we're seeing some really good concepts come from Chinese manufacturers around battery manufacture that, although they're not billed as being designed for recycle, our analysis of those designs looks like a lot of thought has gone into how they're going to be taken apart at the end of life. And in some respects, better than Western vehicle manufacturers, things using cylindrical cells are going to be a complete nightmare at end of life. And I think what we're lacking is some of this granularity between differentiating between, good quality recycling processes and ones that aren't quite as efficient. Peter asked what stage of this roadmap are we at today and what is the timeline that's associated with this into Sherlock. I think probably at the moment we're using a mixture of recycling 1.0 and 2.0 techniques. I think, recycling 3.0, we have lab demonstrators of things that are working. We have a big set of robots that ties the energy part, pack disassembly, one of the University of Birmingham's investments in this area. So we're trialing things at the lab scale, but we need to scale that up to show that it can work at an industrial scale. That's going hand in hand with the fact that, it's not expected that, the vast quantities of end-of-life batteries will reach us for several years yet. So I think we've still got time to do this. In terms of recycling 4.0, that's much more difficult because we need to get traction from automakers really engage with this process. And so I think, this is more of a future ambition. Richard Anderson's asking, how likely do you think it is we'll see industry-wide standardisation to improve the manufacturing design processes to maximise the opportunities for recycling? How could this be regulated? I'm thinking about the difficulties around mobile phone chargers and the lack of interest from manufacturers to standardise. It seems a similar situation could apply to vehicle batteries. And so, yeah, I think that's a great point. I think to some degree, we will see standardisation as a result of manufacturers pooling resources around a common platform. So, when we look at people like Volkswagen, Audi, Lamborghini, Rolls-Royce, Seat, Skoda, they're all part of the same group. And so we see sort of platform sharing and, use of IP across a wide range of vehicles that go into different, marks. And so I think some of this standardisation might be a natural function of the industry, coalescing around, common platforms because there's an economy of scale in developing those. Whether it's possible to get standardisation across the industry, I'm not too sure. It would be nice to think that regulation would be a stick that could be used to incentivise that, but that might be too ambitious. We'll talk a little bit more about regulation as we go on. There's a couple more slides yet. I just see Derek pop up. Are we doing okay for time, Derek? 15 more minutes? I've been trying to take some of the questions as we go.
Yeah, if you're happy to keep going, then yeah, we can continue going.
Good stuff. Okay. So yeah, so we're saying that in terms of recycling and design for recycling, to unlock this best case scenario, it's a case of we need to improve both the recycling processes, but also the pack technology at the same time. And so, it's picking up on the comments from the previous slide. And we've got a paper that's looking to come out in One Earth, where we look at, what might the idealised future designed for recycled battery look like. And there's lots of thoughts in there about how we might integrate data connectivity to be able to get diagnostic information from the battery before, we've actually taken the cell out of the vehicle. This idea of these sort of large, planar, designed for recycle, pack to cell concepts make things very easy to take apart. And so there's a whole bunch of thinking that we're doing around this at the moment. And this concept of digitalisation of lithium-ion battery recycling. So, the more and more intelligence that we can deploy to being able to, analyse the quality of the battery when it comes out, being able to make assessments over to whether to put that into a reuse application, like a second life application, where it gets used in, grid storage, for example, or whether to recycle that directly. The more data we've got, the better decisions we can make. And so we're saying that there's also some parallels. So we're talking about lithium-ion battery recycling in the main, but we're also interested in other critical materials like the rare earth magnets. And there are lots of synergies between these two, different approaches in terms of thinking what we would need to do to disassemble magnets as well as disassembling batteries. And there's work at the University of Birmingham, so this is based around hard disk drives, on how to recycle the magnets that are used in hard disk drives, the same magnets used in electric vehicle motors. And there's a spin-out company called Harper, which is looking at how to commercialise this technology developed at the University of Birmingham. And so what we're saying is that in a future circular economy of electric vehicles, you could imagine there being real synergy between end-of-life recycling for batteries, end-of-life recycling with magnets, common processes around robotic disassembly and automation to take vehicles apart and to separate those materials. But then obviously those materials flow into different value streams for motor manufacturing and battery manufacturing. We talked a bit about regulation. We've done some analysis of the EU battery regulations, which were a step in the right direction here in this Science Policy Forum piece. And here you can see set out, what we think a circular economy of lithium-ion batteries might look like, and also some of the specific elements where regulation applies to different parts of this process. So you can follow it up with that article there, which is quite a nice read. The other thing is that in addition to the technologies used for battery recycling, there's also thinking about the shape and the form of the industry in the future and what that might look like. And so we've done this piece in applied energy, which is looking at the UK circular economy for lithium-ion batteries and modelling that to really look at how to spatially optimise that industry to reduce the amount of transport miles travelled between different nodes, between end users, between end-of-life vehicle processors, and then where might be the optimum places to locate a battery recycling plant, depending on that sort of weighted centre of gravity of where those waste arisings are likely to occur. So I hope you found that interesting. I think there's one more question that I can see from Christine Fernand saying, are other industries looking at your research with a view to incorporating it into their manufacturing? I think certainly within our Met4Tech project, we're looking at challenges that apply across a whole range of different technology metals. And certainly we can see the application of a lot of our different technologies in different arenas. So for example, some of that ultrasonic delamination technique we might look at for future solar cell disassembly, etc. So, there's some options and things that we might be able to evaluate in the future. What industry is doing? Yeah, we've got conversations that are ongoing, but things are all at an early stage as we try and drive the transformation of this industry. So if you want to get in contact, here are all of my details, and if there's any more questions, please type them now.
Fantastic, thanks, Gavin. Definitely interesting. I had a quick question. Do you find that manufacturers are open to having conversations at the design process to try and make the recycling process easier?
I think if you'd have asked me that question 2 or 3 years ago, I'd have said no. I think at that time, industry was just struggling with even trying to get EVs out the door. They'd already placed massive investment in certain vehicle platforms that were new to the market, and they were just trying to see how to get vehicles out the door using the technologies that they've developed. And given how constrained they are for capacity, and given how much resource it's taking to drive the car industry into EV transition, I don't think that was a particularly welcome conversation. I think as time's gone on and manufacturers are realising that there are challenges around securing access to critical raw materials and resources, that's starting to go up the agenda, because people are looking at, can we get the materials from our batteries at the end of life?
And do you find that manufacturers are more open to talking to each other and working with kind of technology that they have and sharing as part of that?
I think, we've seen some collaborations within the EV industry. I mean, even at the start of things, people like Mercedes-Benz and BMW, which, sworn enemies, and they spoke and they said, maybe we should be collaborating. But I think some of those collaborations have fallen apart. I think it's a difficult one, isn't it? Because there's that whole balance between having competitive advantage, and at the moment everyone's trying to secure that advantage based on new products and technology. But in the longer run, perhaps that competitive advantage could come more from, the distance between firms diminishes as technology becomes more mainstream, and then perhaps there's more appetite for collaboration as things start to shake out. And we've just had an anonymous attendee ask if recycling 3.0 would come in within a reasonable timescale. Could it be applied to currently in use designs of batteries and gain a higher quantity of high quality material back from them? Or do we require the design of new batteries taking recycling into account to achieve better recycling? And so I think it's very much our view with recycling 3.0 that we're applying sort of better recycling technologies to some existing batteries. Now, there are some, like I said, Tesla cells, cylindrical cells. I think they're always going to be really difficult to recycle using anything other than shredding or pyrometallurgical approaches. But certainly for sort of pouch cells, Nissan Leaf cells, some of these BYD cell-to-pack cells, I think that there's enormous potential there.
Fantastic, thank you. That's it for the questions I can see. So that's it from us today. Attendees, thank you for logging in. Hope you found it beneficial and informative.